Okay, so I will record this meeting also and I will upload to LMS. Okay, so I will be talking about impedance matching today. So we in the last class we were talking about Smith charts, and we did some introduction to Smith charts. So we learned about the basic features of the Smith chart. So we have this circular chart, which we can divide into using, actually there's a horizontal axis. And there are some circles that we can draw from this right hand side, and each of these circles can be given some value. So all these values that we can mark are in terms of normalized values. If there's some kind of impedance that we are considering, the normalized value of that impedance will be marked in the chart. Okay, so directly the impedance is not marked, but the normalized one is marked. So we will talk about that in a certain example as well. And then in the center of this circle, we have a point called 1.0 point, which is also known as the matched point. Basically what we mean is that in this point, the impedance is 1 plus 0j. That means that the impedance in here is fully real, right? The imaginary part of the impedance is 0. Therefore, if we want to match a certain, a circuit, we try to achieve this point. After doing all the matching, we try to achieve this point at the end. So anyway, so this is known as the matching or match point. This right hand side furthest point on the horizontal axis is known as the open or short circuit based on the chart that we are considering. So for an impedance chart, that means Z chart, we can see that we have Z going to infinity in here, which means open circuit position in here. So if we take a transmission line or some kind of a line which is having an open circuit at end, we take that open circuit point from this chart as this point. So we will do some example, and I will be able to explain you more clearly in that situation. And then in here we have the short circuit point, right? So we have the short circuit point in this place where Z is equal to 0. Right, so Z equals 0 when there's a short circuit, right? So at that point we have the short circuit point. So basically, apart from that, we always need to mark the impedances as a normalized impedance. So always we need to mark normalized value of the impedance. So if we take a certain impedance ZL of a certain load, we need to divide that ZL by the characteristic impedance of the line, and then we need to take the normalized impedance, simple ZL, which will be division of this real or the load impedance by this characteristic impedance. So we need to get this normalized impedance, and we need to mark it in here. So those are the basic things we learned about in the last class. Now coming to this point, now we are trying to solve some real problem related to the transmission lines using the Smith chart. So once we talk about the real problems, so one of the problems we have is that we we do not have the ability to match the circuits very easily to certain loads using the quarter wave transformer or other matching methods. So once we have very complex loads, then sometimes we might not be able to easily match our load to the transmission line. So if we take, for example, we have a certain like microstrip antenna. Now, this is some example I always take. However, like we can take the microstrip antenna where we have the so this is the antenna part. This square patch or rectangular patch is the antenna part, and the feeding line, there's a feeding point in here where we supply some kind of a power, or we connect this point to another circuit in the rest of the circuit. So in here we have a transmission line, and this transmission line needs to be connected to this antenna in such a way that we deliver the maximum power to the antenna. So maximum power transfer is what we are expecting. However, we might have some impedance differences between the transmission line and the antenna, right? So due to the impedance difference between the antenna and the transmission line, we have power losses, right? So TX line and antenna, we have power losses, and because of that, we are facing like cost-wise, we are losing. So therefore, we need to do impedance matching as a solution, right? So as a solution, we need to do impedance matching, and by impedance matching, we can reduce the power losses, right? So there are many type of impedance matching that we can use. So in this class, we will be basically looking at two types of impedance matching, which are the first one is the quarter wave transformer based impedance matching method. So we learned about quarter wave transformer, I think, right? We learned about quarter wave transformer based matching. So basically in quarter wave transformer, what we do is we connect a certain transmission or conducting line of a certain length in between the load and the transmission line. So in that case, like what we do is that if we have the same circuit as here, then we have the transmission line, and then we connect a certain like a piece of strip of a certain length and width um, before connecting our circuit to the antenna. So it could be, I mean, this length is negligible. So we have this is the quarter wave transformer, and then we have the antenna. So like this we can take the antenna, like this we can take. So so basically we are connecting a piece of transmission line of certain length that we decide of, which corresponding to lambda over 4 between the transmission line and the antenna. And by doing that, we can actually achieve some kind of matching, but in this case, this length that we fix in here is fixed for all time. So once we have fabricated this circuit, it's difficult for us to change this matching. Like sometimes it's very difficult to do any changes to this matching circuit because this length is fixed, and whatever the stub we have made is fixed. However, like this is also so actually that is okay. I mean, since we have in stub matching also we have such kind of problems where we fabricate the stub, and after that we can't change the location of the stub. So the disadvantage in here is mainly because this quarter wave transformer is acting only for one frequency or a single frequency. So because of that, this quarter wave transformer cannot be used for many like frequency ranges. So this will work for certain frequency like a certain carrier. For a single carrier transmission, we will be able to use this. For applications where we need to use the same antenna for different frequencies, we might not be able to use this kind of a matching circuit based antenna. So in that case, we need to go for other situations where we can actually use the same circuit for different frequencies. So in those circuits, we use stub matching as the matching technique. So stub matching is done using the help of Smith charts. Okay, so that is basically regarding like how we can do impedance matching. So do you have any questions so far? Do you have any questions? Please let me know. Okay, so then we will actually try to talk about the stub matching. So stub matching is actually a very broad technique. There are many methods of doing stub matching. So stub matching can be done in single stub matching, we call, right? Single stub matching can be done, double stub matching can be done. Basically, single stub matching means there's only one single stub which is attached to the transmission line. In double stub matching, we are adding two stubs to the transmission line. So, for example, again, I will take the same example that I always take, the microstrip antenna, where we are having the stub connected to the antenna. So in here, we have a transmission line, and the transmission line is connected to the antenna. So we are in here, we will say we are feeding. So this is the circuit. So in here, we can add the stub. We are adding a certain metal strip in here at a certain distance from the antenna and with a certain length. We know this length. So we know the length, width, and the distance that we need to place the antenna in. So, sorry, stub. This is the stub. So we do some stub. We add some stub here, and this is known as stub matching. And when we have double stub matching, we just have two stubs like that. We have two stubs like that. So we have like this, and we have two stubs like this, which are separated by a certain fixed length. Okay. So this length could be lambda over 8 or something fixed. So when we have two stubs, we call that double stub matching. When we have one stub, we call as single stub matching. So that is one category where we can categorize the stub matching. There are like, furthermore, we can do it. Okay, so each of the stub matching, single or double, we can again divide into two parts, right? The single stub matching, we can divide into two parts called as series stub matching and shunt stub matching. Shunt or parallel. Okay, shunt means parallel, right? Shunt, the word shunt means parallel, right? So if you don't know, you can get it clarified. So every type of matching, single or double, we can divide into two: series stub matching or shunt stub matching. So what is the difference between those two things? So I will draw again another diagram. So once we have the transmission line, if we connect in parallel to the load, then these diagrams that I drew were about parallel stubs. So we can actually, I can draw in two ways. This one, I can show that this is parallel stub matching, right? This is parallel stub matching where I create the stub. So the top part of the stub is on the top plane, and then the rest of the stub is connected to the ground plane. Okay, so in once if I draw this in another way, this is, let's say this is the antenna. This is the antenna load, and I will be connecting the stub as in parallel to the antenna load. So in parallel to the antenna, I connect the stub. So the stub, this part is what I'm drawing here. The top part, only the top part you can see from the top view, right? I can connect these two conductors across the microstrip board. So this part you can't see. You can't see in this diagram. And this conductor is a ground conductor, ground plane, right? Ground plane. This corresponds to the ground plane conductor, right? Or ground plane actually, because the ground conductor is a whole plane, not a single conductor, but entire plane, which is known as the ground. Right? We only need to define the top conductor. The ground plane will remain the same for any type of number of top conductors. There could be multiple top conductors. So this is the top conductor. Right? So this is the bottom conductor, ground plane conductor, bottom one. Right? So in between, we can connect this using some metal, some kind of a connection, maybe coaxial connection or some kind of metal conductor we can add here, or else we can leave it open circuit. This could be short circuit or open circuit. Depending on our requirement, we can leave it short circuit or open circuit. Okay, so I'm not that good in arts, so I need to, like, I can draw this in different ways actually, in order to clarify this idea. So this is the top view, and if I draw this in the side view, the top conductor will be like this. Top conductor will be like this. Ground plane will be like this. Ground plane will be like this. The antenna is somewhere here, right? So if you are adding the stub somewhere along the top conductor somewhere here, the stub will be here, and its corresponding ground plane will always be the ground plane. There's no difference in the ground plane. So the antenna will be somewhere here. Antenna will also be here somewhere. So this is the antenna part. This is the transmission line. This is the stub. Likewise, the components will be there on the top, and in between we have the dielectric material in here. So that will separate the top conductor and bottom conductor, and the ground plane will be like this. I hope it is clear to you. And the stub will end here, and the stub can be connected to the ground plane using a metal conductor if needed. Right? If needed, if we want to short circuit it, we will be connecting those two with a metal conductor in here. If we want to short circuit, otherwise we leave it free. We don't connect this top stub and the ground plane if we want to connect in open circuit condition. So those are the options that we have, right? So as I said, we can connect each of these stubs in series, and also either as open circuit or closed circuit, right? Short circuit. Each of them we can again divide into two parts, open or short, right? Likewise, I can divide it then, right? So those are the basic ways that we can do stub matching. So as you can see, there are many variations of stub matching. So do you have any questions regarding that? So those are basically theories. So we will start with some example, right? We will start with some example. So I did not draw this series single stub matching. So series stub matching, I will draw how it is shown in the microstrip lines. So if we have the basic microstrip line like this, the series stub matching will be shown like this, right? Earlier I showed you the parallel stub matching. The series will be connected in this manner, where top conductor will connect in two places to the transmission line. So the transmission line will be like this. So we have a certain distance between these two connections as well, some fixed distance that we can define. We need to have these dimensions, and we need to have the dimension of the distance from the antenna to this point, and the length that we need to drag this stub towards the other direction. Okay, so this length L, which is the length we need to draw the stub or drag the stub along the perpendicular direction to the transmission line. So this is how a series stub matching will look like on top view. Right, so basically we will be doing one question about series stub matching and one question about uh, shunt stub matching. Okay, so shunt and series stub matching we will discuss in detail. Okay, so first we will do one question about shunt stub matching, and we will try to use the Smith charts. So shunt stub matching procedure. Okay, shunt stub matching procedure. Right. So the procedure will be like first, you need to first, now you are trying to now let's assume we are trying to connect our transmission line to a certain load, right? So we have a certain load of ZL, capital ZL. That capital ZL will be 60 minus 80 J ohms, right? And then the transmission line is this one, and its characteristic impedance is 50 ohms, let's say, right? So first, what we need to do is we need to normalize the load impedance. Right, so normalize the load impedance means what? What do we need to do? We need to, is it not? Yeah. So you know the two values, right? So you can do that, right? So ZL is 60 plus 60 minus 80 ohms. The normalized ZL or simple ZL, I will denote it as simple as with a dash in between, will be the division of this by 50, right? So what is the value that you get once you divide it? So you can use your calculators to divide these kind of complex numbers. One thing, if you are given the ability to access MATLAB also gives really accurate answers. So you can find the answers to these ones. So what is the answer did you got? Yeah, 1.2. Yeah, 1.6. Yeah. So this is the normalized impedance that you will get, right? So next, you need to draw your Smith chart, and you need to draw the corresponding SWR circle of that point. Draw the SWR circle related to of ZL, right? So first you go to the Smith chart and mark this point. Okay, so once you are marking that point 1.2, first you need to mark the 1.2 circle in the impedance circles, right? 1.2 circle you need to first select, and then minus 1.6. Minus are available in this bottom side, right? You need to select the 1.6 line, and then you need to take the intersection between these two lines, one circle and the line. Is it okay for you? You can do that, right? You just have to be just read these circles, values of the circles. There's values of the circles, right? So you have circle like from 0. So this is Z equals 0 from that point. Okay, so we will move to the next step, right? So is it clear that impedance pointing thing is clear, right? So it's not that difficult, right? You can read this chart, you can do it very easily. So next important thing is you need to consider admittance chart. I will write it, right? Now for shunt stub matching, right? For shunt stub matching, you need to consider the admittance chart, right? So you will ask why you need to do that, right? So I will explain. We consider the admittance chart, right? We consider the Smith chart in its admittance form, right? Smith chart as an admittance chart, right? So admittance means 1 over impedance, right? 1 over impedance, right? So the reason is that now we are going to do a shunt stub matching. Shunt means parallel stub matching, right? So we are going to connect a certain stub in parallel to the load, right? So somewhere in between this line, we are going to connect a parallel load to this transmission line, right? So the impedance and the stub will be in parallel to each other, right? So once we are going to match these two impedances, we want to take the sum impedance, right? Once we are taking the sum impedance, rather than taking the impedances itself, once we take the admittance value of these impedances, we can directly add these values. Now, if the admittance of this impedance is YL and the admittance of this stub is, let's say, YS, we need to add these YL and YS and get some real value as the output, right? So we want to cancel out all the imaginary parts. So we want to get some real value. So real value, which is some number, which is not containing any kind of a imaginary part, right? So in order for us to do that calculation, is very easy if we have the values of these impedances in admittance form. So therefore, we directly convert our load into admittance form. Then from that only we do the calculations, the rest of the calculations, right? So we find the like the impedance or the admittance of the stub also in admittance form. So because of the easiness of the calculations, we convert our load into admittance. And then we do the rest of all the calculations in admittance form, right? So in the first step, you found the impedance value and you mark the impedance value in this chart, and this is the impedance value, right? So in order for us to find the admittance value, we need to do something. How can we find the admittance value? So what is the very shortest method? If the impedance is here, we can take the same, like we can take the magnitude, then we can take the 180 degrees shift, and we can draw, like we can draw a line across the 1.0 point. Like in here, actually, I can't draw this correctly, but in here, right opposite, the point which is very opposite, correct, I mean 180 degrees opposite to this impedance line will give you the admittance point of that line, of that impedance, right? So if we have the impedance in here, once you take the ruler, you can take the ruler and take the opposite point on the other side of the like maybe the Smith chart. Once you go across the 1.0 point, can you understand what I'm saying? Right? Directly මේ consider කරන point එකේ opposite point එක ගන්න ඕන. අර 1.0 කියන point එක through line එකක් ඇඳලා ඔයාට හරියටම 180 degrees shift වෙන point එක ගන්න ඕන. එතන තමයි ඒ කියන්නේ මේ හරියටම අරකේ 1 over value එක එන්නේ. හරිද? ඒ කියන්නේ දැන් මේ Smith chart එක හදලා තියෙන්නේ ඒ විදිහට. මොකක් හරි impedance value එකක් තියෙනවා නම් ඒකේ 1 over value එක නැත්නම් ඒකේ admittance value එක එන්නේ ඒ point එකේ opposite point එකෙන්. ඒ opposite point එක ගන්නේ හරියටම ඒකේ 180 degrees මේ shift වුණ point එක. Okay. Is it clear or like just ඒ කියන්නේ 1.0 point එක තියෙනවනේ හරියටම නේද? ඒක through යන්නේ. Then you can directly get the exact can a straight line එක ගන්න පුළුවන්. ඒ කියන්නේ I explained this I think in the last class. I don't know whether you can remember. You can okay, so do you get a point like that? You get a point like that. So magnitude එක එක්සම වෙනවා. අර magnitude එක අපම මෙතන කියලා And you can check also that actually the actual value of the so it's okay for you, right? That part. Then you need to extend that point, extend that YL. The YL is the admittance point, okay? Let's mark it as simple YL, right? So extend that YL point, YL point, right? Extend the SWR circle of the YL, okay? So extend the SWR circle of YL point until it intersects the unit circle. Right? So why are we taking unit circle? We will ask, why are you taking unit circle, right? So now the thing is, now we are trying to match the transmission line to the impedance, right? We are trying to bring the impedance value to a real value, right? To a real value, right? So the real value we can gain by moving as much as possible towards the unit circle, right? So the unit circle is a circle in the Smith chart which has the value of 1 plus jx. If we take the impedance value, there are different circles, right? In the Smith chart, we have different circles, right? So there's a circle which is 1.0, right? There's a circle with the value 1.0, right? That circle is known as the unit circle, and that's a very special circle. Okay, so wherever we have our impedance, our load impedance could be anywhere in this chart, but we are trying to bring that load impedance near to this unit circle, because we want to finally reach the point where the total impedance is 1. We are trying to make the total impedance 1. So we are trying to go to the unit circle, because the unit circle has the impedance of 1 plus jx. No, that 1 is there. We just need to cancel the jx part. We will do that in the second step. But we are trying to move our load impedance wherever it is towards this unit circle. So because of that, we have now our load impedance somewhere here. We are trying to move that from this point to the unit circle, right? So unit circle is somewhere here, right? So try to draw the unit circle, right? So I will, so try to, first you need to draw the SWR circle of the YL point. YL point is the admittance point, right? So admittance point, in there you have you can draw the circle from this center point, and you can take the radius and you can draw a circle, right? You can draw a circle using your compass, or you can use the circles available in the Smith chart. I don't know. I think it's not available. It's not available. So you need to take the circle with this radius, and you need to draw the circle until it intersects the unit circle. There's a unit circle with 1.0 and 1.0 value. Until you intersect this circle, you need to extend this YL point. So you need to find this intersecting point. And there's not only one intersecting point, there are two intersecting points. You need to find both the intersecting points. So my diagram is getting a little bit confusing, but you need to just extend the circle until you meet the unit circle in 2 points. Right? So can you do that? Do that. So, did you understand what I said? Okay, so did you all mark the intersecting points, right? You can stay, right? You know the method, no? You do it with the compass, right? So try to find the compass later and you do it. It's okay, you don't have to do it. For the moment, just you don't have to do it. Later you can do it. Now the important thing next is that you need to measure the distance from the YL point towards the to the intersecting points. You have two intersecting points. Let's mark the two intersecting points as Y1 and Y2, right? So from YL, you need to measure the distance to Y1 and you need to measure the distance to Y2, right? So two distances you need to measure, right? So those two distances we mark as D1 and D2, right? So those D1 and D2 will be the distance from the load to the stub point, right? So either we can attach the stub at D1 point from the load or D2 point from the load, right? That is the significance of these two distances, right? So this is very important measurement that you need to make. So these are the parameters that define where we need to place the stub in the transmission line, right? So D1 you need to measure, right? So from YL only we need to start, right? So why don't we start with ZL? Because we are, as I said, we are going to match the match using admittance values. So therefore we are going to start from the admittance value of the load YL and mark the distance from YL to Y1, right? So the distance you can measure from the outer scale, right? There's a outward scale at the very outer edge of the Smith chart. There's a scale, right? Where you where it is shown that you can measure the wavelengths towards generator, right? Wavelengths towards generator. There's a scale called wavelengths towards generator, right? Wavelengths towards generator, right? Do you find that scale? Right, so that scale will give you a distance in terms of lambda. In terms of lambda, it will give you wavelengths towards generator, right? So what do you mean by wavelengths towards generator, right? Once you are moving in this direction along this scale, then you're moving from the load towards the generator. The generator is the kind of the source. Source is known as the generator here, right? So once you are going from the load, you need to go from the load towards the generator, right? So in that case, you need to measure the distance in the like clockwise direction, right? Distance kind of load point එකකින් ඉඳන් generator side එකට යන්න ඕනේ නේ. එතකොට generator side එකට යන්න නම් අපිට මේ scale එකේ clockwise direction එකේ යන්න ඕනේ. හරිද? මේ scale එකේ තියෙන්නේ towards generator කියලා ඊතලයක් ගහලා තියෙනවානේ outer scale එකේ towards wavelengths towards generator කියලා outer scale එකේ scale එකක් තියෙනවානේ ඊතලයක් ගහලා තියෙනවානේ මේ පැත්තට යන්නේ කියලා generator එකට යන්න ඕන නම් දැන් load එකේ ඉඳන් ආව පටන් ගන්නවා generator එකට යන්න ඕනේ මේ පැත්තට යන්න ඕනේ ඔයාගේ measurements stub එක කොහෙද place කරන්න ඕනේ කියලා හොයන්න නම් load එකේ ඉඳන් ඔයා generator එකට යන්න ඕනේ නැතුව generator එකේ ඉඳන් load එක නෙවෙයි ඒ නිසා ඔයා ඒ පැත්තට තමයි ඔයා measurement එක කරන්න ඕනේ. හරිද? එතකොට හැම වෙලේම ඔයාගේ load point එක තිබ්බේ කොහේ හරි මෙතන නම් එතන ඉඳන් අර intersect වුණ point එකට මේ පැත්තේ ඉඳන් තමයි මනින්න. clockwise. හරිද? clockwise distance එක තමයි මනින්න. හරි? බැරි වෙලා හරි ඔයා එතන ඉඳන් anti clockwise direction එක මැන්නොත් ඒ distance එක වැරදි. ඒ කියන්නේ ඔයා මේ load එකේ ඉඳන් ආපහු load එක පැත්තට යනවා කියන එක. එහෙම නෙමෙයි ඔයා load එකේ ඉඳන් generator එක පැත්තට යනවා. හරි? එතකොට මේ intersect වෙන point එක හොයන්න ඕනේ මේ direction එකේ ඉඳන් ගිහින් තමයි හොයන්න ඕනේ හැම වෙලේම. හරි? එතකොට intersecting point දෙකක් තියෙනවා. එකකට ඔයා මෙහෙම හොයනවා. ඊට පස්සේ ඊළඟ එකටත් ඔයා එහෙමම හොයනවා. මේ impedance point එකේ ඉඳන් ඊළඟට intersect වෙන point එකට මෙතන පටන් ගෙන ඔයා මෙහෙම ගිහිල්ලා මෙතනින් ඉවර වෙනවා. එතකොට ලොකු distance එකක් දෙවෙනි point එකට. හරි? So you need to find that length in terms of wavelength. wavelength වලින් කීයක්ද කියලා හොයන්න. හරි? එතකොට පටන් ගන්න point එකේ පටන් ගත්ත point එකේ මේ location එක මේ scale එකෙන් හොයාගන්න පුළුවන්. ඊට පස්සේ ඉවර වෙන point එකේ point එකත් ඔයාලට scale එකෙන් හොයාගන්න පුළුවන්. ඒකේ difference එකෙන් තමයි distance එක හොයන්නේ. Right? So you can find the distance by taking the difference between the locations of the 2 points. Right? Intersecting point එකේ location එක තියෙනවානේ මොකක් හරි lambda value එකකින් මෙතනින් එනවනේ. A point එක minus මෙතන load point එකට අදාළ wavelength එකේ මොකක් හරි point එකක් එනවනේ එතන 0.08 වගේ value එකක් එනවනේ ඒක minus මේ ඒ value එක ගන්න. එතකොට දැන් ඔයාලගේ මේ question එකේ දැන් intersecting points දෙකක් තියෙනවනේ. first intersecting point එකේ length එක තමයි 0.176. 0.176. එතකොට ඒක තමයි අර y1 එකේ location. y1 එකේ location point එක. ඊට පස්සේ yl එකේ location එක තමයි මේ 0.065. මේ ඔක්කොම ඉන්නේ lambda වලින්. හරිද? මේ ඔක්කොම ඉන්නේ lambda වලින්. ඒකේ value එක ගත්තාම අපිට ඒකේ difference එක ගත්තාම අපිට value එක ගන්න පුළුවන්. Right? We can take the value as 0.111 lambda, right? So we need to take the difference from the intersecting point and we need to take the difference between the intersecting point and the admittance of the load point, right? So we need to take the difference between the intersecting point and the load point. So that difference will give you the distance that you need to move from the load point towards the stub point, right? So this D1 is given by this distance, right? So if we know the frequency of our waves, then we can find the value of lambda. If we don't know the frequency, we can leave it as it is. And then D2 value also we can find similarly. We can find the intersecting points location in terms of lambda, and we can reduce the location of the load, and we can find the distance as in terms of lambda. So we have two values, D1 and D2, right? So we will ask, like, why do we need two distances, right? So there are two options that we can use. These are the two options. This is option 1. This is option 2, right? We can use any of the options. If we like, we can use D1 for our design, or else we can use D2 for our design. Right? So we can proceed with any of these two options. Once we select one distance, we need to proceed with that distance in our next calculation of the length. Now, after finding the distance, we need to next find the length of the stub. We need to decide the length of the stub, L1, let's say. L1 we need to decide, and that also we can do using some more calculations, right? So so we will discuss about that in the next class. So that's a very small part that needs to be done, but that also needs some focus. So we have today in our class, we have found how to find the length to the stub, how to find the distance to the stub from the load point. Okay. So with that, I will end today's class. Okay. So if you have any questions, you can let me know.